First of all, thank you all for coming. This is quite a packed room. I wasn't expecting so many people, so it's great that you turned up. I'm here to talk about improving system resiliency via chaos engineering. Let's see if my clicker works. No, clicker's not working. Bear with us. Clicker's stopped working.
Resilient.
Yeah, right. We need to chaos engineer clickers. Oh, we're back. Okay. Marvellous, thank you. Just a quick bit about me before we begin. My name is Joseph Woodward. I work at Just Eat. I've been doing software engineering now for about 10 years or so. I'm quite vocal on Twitter. You can find me online if you don't have time to talk to me after this. Before we begin, a rather eloquent quote here by Margaret Fuller. If you have knowledge, let others light their candles with it or in it. I started speaking about 3 years ago with the New Year approach, and I'm sure a lot of you probably have some sort of New Year's resolutions. Anybody out there interested in speaking? It's definitely something I would recommend. You know, one of the great things about this community is how good we are at sharing knowledge. You know, I never went to university. A lot of what I've learned has sort of been taught or learned via books, the internet. You know, we're kind of approaching an age now where we're not self-taught developers, we're community-taught developers, and being able to share that knowledge with other people is a great thing to do. There are lots of ways you can do this. As BrizTech, for instance, you know, local meetups is a fantastic way to get started, so it's definitely something I would encourage. So moving on, once upon a time, about sort of a decade or so ago, systems looked rather like this. They were simple monolithic applications. A lot of you probably still deal with these kind of systems. They were fairly sort of trivial in terms of complexity. Obviously, you had the complexity of the code, but in terms of the operational complexity, they were fairly straightforward. They were a simple system with a database. And then as things start to grow, more and more teams start to work on these systems, and you start to have issues with sort of conflicts, teams stepping on one another's toes, sort of editing the same code. And then along comes the cloud, and that starts to change things a bit. You know, compute starts to become really, really easy to set up. There's no longer a case of waiting days or weeks for additional systems to be set up. You know, you can provision it really, really easily in these cloud providers. And then we sort of have another stab at SOA in the terms of microservices, where we have this opportunity to sort of tear apart our growing applications, and you can have these sort of multiple teams working on their own components that they own. This simplifies a lot of people problems, which is kind of what microservices was about, but then it also does go a bit further. You know, at this point now with sort of microservices, we've got the improved scalability, fault isolation, lots of other benefits. Localized complexity. This isn't a talk on microservices, so you know we'll move forward. But essentially, at this point, your microservices, you're sort of fulfilling that buzzword, microservices. Out of interest, anybody here doing microservices? Anybody considering microservices? Okay, all right, great, good split. But as the system grows in size, they inherently grow in complexity as well. And this talk isn't limited to microservices. Any system as it grows in size increases in complexity. With the advent of things like serverless, AWS Lambdas, Azure Functions, systems generally are becoming more and more distributed. And with this distribution comes other problems. We've got architectural complexities, operational complexities we have to start thinking about, you know, how do we monitor our system? We've got issues with the data consistency, and then also trade-offs when it comes to the CAP theorem. You know, do you favor consistency versus availability and partition tolerance? And generally, this increases complexity and then increases the ways in which systems can fail. And as you start to approach this territory, you start to realize you start to come across the 8 fallacies of distributed computing. Anybody here sort of recognize the 8 fallacies of distributed computing, or is this generally all new? Fantastic, that's good then. We'll go through them. So the 8 fallacies of distributed computing originally sort of presented by Peter Deutsch, who worked at Sun Microsystems back in sort of 1994. He came up with these ideas. Originally it was 7, but they sort of tacked another one on at the end. The first fallacy, network is reliable. You know, if you ignore this fallacy, then you have to be aware that you're going to face things like packet loss and disconnects. You know, these are quite common when talking across networks. Latency is another problem. Anybody playing online games will be very familiar with this fallacy. Latency is a big issue in any kind of high throughput, low latency environments, things like timeouts, cascading failures can occur. Bandwidth is infinite. This can sometimes lead to bottlenecks in systems. Network is secure. You know, we all know or we should all know by now that security is imperative, and you know, networks are sort of and go and cross network as a means for attackers to be able to get in. And the other one's topology doesn't change. There is one administrator, transport cost is zero, and network is homogeneous. Kind of all lend to these initial problems that kind of come from these four. And as we start to run into these issues, now our system starts to grow, you start to realize at that point that you're approaching the realm of complex systems. But luckily, when you start looking around at complex systems and what they mean, there is a lot of investigation in this area. You know, this complex systems goes beyond just computational systems. And as you start looking around sort of the work that's being carried out by thought leaders in this space, there's one person you come across in particular called Richard Cook. Now, originally, when he started, he was working at the University of Chicago, and he spent an awful lot of time working on complex systems in other industries, such as the health industry, areas where failures cause massive issues. You know, they can cause people to die, or they can cause sort of really bad catastrophes. And off the back of this work, one of the papers he published was this one, called How Complex Systems Fail. It's a rather large paper, but he also sort of summarized it in these key points, which some of them we'll go through in a moment. But he basically sort of proposes the idea that by default, complex systems, we should change the way we think about them. And instead of considering that them working is the norm, we should flip it on its head and think about them how sort of failure is the norm. They start off as failed. And as humans, we put process and things in place in order to ensure that they work. When he talks about complex systems or any system, we think as developers of us here, we think of in terms of programmatically a system. But when you start thinking about what the user perceives as a system, it's also all the people that help make that system what it is and make it work. An idea he proposes at the end of his paper is complex systems are intrinsically hazardous, which drives over time the creation of defense mechanisms against these hazards. So these defense mechanisms come in all shapes and sizes. There are technical sort of implementations we can do to drive defenses. So for instance, we have TCP versus UDP. You know, there are properties in TCP communication which mean it can deal with packet loss and re-establishing connections. And these mechanisms are there to ensure that your connection goes from a default failed state to an actual working state and remain working, even though these regular issues are occurring. In terms of defense mechanisms, we also create training for members of staff as to what to do to make sure things continue to operate in the correct manner. So this isn't just about sort of technical side of systems. This is also human problems. Ultimately, complex systems are not just about technology. With any complex system, we've got the system as we know it, but then we also have this other system that plays a key role in managing that system. Where I work at Just Eat, we have somebody called SOC, which are responsible for kind of monitoring and making sure the system, our distributed system, is working. I, as an engineer, I regularly go on call as well to ensure that our systems remain working. If they exhibit any behavior that is questionable, we've got automated alerts that will page me to tell me that something is potentially going wrong and I need to investigate it. And ultimately, what we start thinking about when it comes to complex systems, we start thinking about the human factors. You know, how as humans do we also influence the systems? That's not to say that the technology side isn't important, but it's just to recognize before we continue that humans play a big part in reliability as well. You know, this can be seen time and time again. This headline, in 2012, Twitter outage caused by human error, domain briefly yanked. Amazon's massive AWS outage was caused by human errors. You look throughout history and throughout some of these large outages, and some of them are sort of automated systems going down, but some of them are caused by human error. This ultimately kind of affects the reliability of a system, regardless of whether it's technical or caused by another person. So ultimately, he kind of comes to the conclusion that you build things differently when you expect them to fail. Failure is a normal state. Failure is normal. The failed state is the normal state. Failure isn't an exception. You know, failure is inherent in what we do, and we have to recognize that. So when we talk about resiliency, the term resiliency is a very broad term. We looking at, in the dictionary, the capacity to recover quickly from difficulties, from toughness, and that sounds all well and good. But in terms of influences that we can sort of press against our system, like what does that look like? And there's been a lot of research in this area as well by the means of this paper, the 4 concepts of resilience. And they kind of delve into resiliency and what it means in a technical sense and the behaviours you'd expect to see from a resilient system. You hear terms like anti-fragility thrown around, but this seems to be a bit more specific about what you should expect. And in the end, they come up with these 4 principles. Some of them have overlap. Principle 1, robustness, how our system absorbs wider and wider range of disturbances without breaking. Number 2, adaptive capacity, our system's ability to adapt and grow in response to dramatic changes in its environment. This is the ability to sustain during changes and to continue operating how it's expected. And bearing in mind, we're not talking about technical solutions here, we're also talking about people. When outages occur, how do people respond to these outages? Something happens, what do those people do with the expertise they gather? The ability for a system to recover from trauma back to a state of equilibrium. Okay, the system goes down, but then the people system is there. How do we get the system back up and running? All of that plays a part. And then graceful extensibility, the system's ability to stretch and grow in response to surprises. This is kind of microservices. This is one of the things that microservices definitely help tackle, because microservices have the ability to effectively scale out. With things like auto-scaling as well, this process can be automated. And using these principles, we can start looking at chaos engineering as a way to kind of exercise and test these principles. Now, hands up here who recognises sort of chaos monkey. You hear chaos engineering, everybody's gut reaction is chaos monkey, and that's certainly true. Chaos monkey is sort of an important milestone in what chaos engineering is. There's also the Simian army. Anybody recognise the Simian army? Okay, so the Simian army is a suite of tools that came after chaos engineering, again, to try and sort of force chaos on Netflix's sort of large systems. So what about the name, chaos engineering? I'm sure a lot of you, if you don't know what chaos engineering is, it sounds like quite an interesting term, doesn't it? It sounds quite sort of radical. On one hand, you've got the sort of the chaotic side, which sort of elicits thoughts of like, it sounds exciting and mischievous. A bit like this guy, you kind of think you can be a bit of a cowboy, go into a system and start breaking stuff. But on the other side, the opposite side there, we've got engineering, which kind of is disciplined and structured, which makes you think of engineers and scientists and actually having some kind of discipline in what we do. And kind of what does this look like as an actual practice, as a discipline? So chaos engineering itself originated from Netflix. There was a small team there, the SRE team, which have eventually kind of evolved out into a dedicated team. And this is a free book they published online, which I definitely recommend downloading and reading. It's not too long, but it really summarizes chaos engineering and how you can roll it into an organization, how you can get buy-in from the company and peers. And the definition they've got, which is an early definition, it still holds true, but as a discipline, it's evolved a lot since then. They say chaos engineering is a discipline of experimenting on a distributed system in order to build confidence in the system's capacity to withstand turbulent conditions in production. Simplified and a more sort of modern approach is the goal of chaos engineering isn't simply to find vulnerability and reduce outages. The goal is to be more prepared for the turbulent conditions when they inevitably occur. Going back to this original paper about how complex systems fail, failure is inevitable. Everything fails at some point. And chaos engineering is how, as developers and as companies, we can be there to handle those conditions and be prepared. In practice, chaos engineering is about controlled and planned experiments. It's not about just going breaking things willy-nilly, pulling wires out. That's not productive. You don't learn from that. It's about discoverability, understanding what your system looks like and how it behaves in failures. And it's about preparing for unpredictable behavior. Anybody working in sort of large distributed systems will know some of the issues that can occur. A bit of a timeout can cause these cascading failures throughout a system. They can cause queuing or sort of overutilization of resources, which then kind of propagate throughout the system with this fascinating rippling effect. It's understanding how your system behaves under these different stresses inherent in distributed systems or in any complex system. And it's also about preparing humans for failure. You recognize that humans is a big part of that. And they play a large role. A great quote here from Chris Pinkham, who is the original EC2 engineering manager at AWS about a decade ago. He said, you can't legislate against failure. Instead, what you should do is focus on fast detection and response. So not every failure scenario can be written down in paper. There's an infinite amount of variability out there, and you can't imagine every single failure scenario. It was not so long ago, there was a large ISP who let a domain expire. A simple mistake as letting a domain expire caused their whole system to go down for a whole day. And the only way they could reach people, this is emails included, the only way they could reach people was actually via Twitter to make an apology, just out of a domain expiring. It's not the kind of thing that you would necessarily imagine when you think of a failure. So what we should focus on as well is the ability for teams to be able to detect these issues quickly and then respond to them. So chaos engineering also plays a way in exercising that. Chaos engineering is not about random engineering experiments. It's not about just pulling plugs. It's not about unsupervised experiments either. You need to talk to people to let them know what you're doing and kind of what kind of failure scenarios they might see, so they can be prepared. It's not about unmonitored experiments. Again, it's about visibility. If you start running experiments, which we'll go through in a moment, it's about ensuring people have a visibility of what you're doing. And it's not about breaking production. You hear the name, it sounds quite glamorous, but it's, we don't want to go into production and start breaking things willy-nilly. We're not all Netflix. We can't have a chaos monkey randomly tearing down instances. If as an organization you reach that size, fantastic, but it's not part of this. Ultimately, chaos engineering is about testing proactively instead of waiting for an outage. It's funny because the developers here, we test our system to prove behavior in our system, but then we ignore the behavior it exhibits in the case of an outage. We'll roll out sort of resiliency patterns like circuit breakers, but how often do we actually test those and ensure that the system operates as expected when rolling those patterns out? So some of you might be thinking, why would you break things on purpose? It sounds rather counterintuitive. But when you look, when you look around, it's actually something we do quite often. We vaccinate our children. Like a vaccine, we inject harm into their bodies and into our bodies to allow our system, our body, to build immunity to these things we're injecting them. So what does a chaos experiment look like? First of all, you have to form your hypothesis. How would our system behave if a downstream service fails? What if we see latency in responses from a downstream service? How does that affect our system? This is something we see quite a lot with a certain number of systems. If there's a little bit of latency, what does it look like as that latency propagates up, as it starts sort of reserving resources, sort of causing queuing up the rest of the system? How does everything above that service behave? And then more extreme scenarios. What if AWS S3 goes down? Some of you might think AWS is powering the internet. S3 won't go down. And then there was this, which took down half the internet. It took down an awful lot of the internet. There's a lot of services relying on S3. And that human error I was talking about earlier, about the command line argument, this is what caused this outage. It was a command line argument by a developer that was able to take down S3, a fundamental part of the internet. There's so much hosted on it. As a new developer who was able to go in there, run a command line script that he was told in this documentation, and it took down a huge part of the internet as a result, just from this engineer following instructions. A lot of us will think, well, what is he doing, being able to take down S3 via command line? But these things do happen. So once we've got our test, we can then create a hypothesis. How do we expect the system to behave when we run this experiment? So we introduce some latency between two services. How do we expect our system to behave? And then you run your experiment. Now this is a tricky part. This is where kind of tooling comes in. You really have to think about how you can do this. We'll go through tools later on, but there are some there to enable you to run these kind of experiments. But ultimately, when you run your experiment, you want to measure the impact that this has. What actually happens. And in doing this, the first thing that's important is to control your blast radius. As an experiment, we want to be disciplined. We don't want to be causing people issue. One of the pioneers of chaos engineering, a lady called Nora Jones, who works at Netflix, does a lot of talking on chaos engineering. She used to work at a company called Jet in America, and when they started chaos engineering there, they did it in a QA environment, and she ended up, or they as a team ended up taking down Jet's QA environment for a week as a result of a simple chaos engineering experiment. So this is why it's really, really important to be disciplined and ensure that you control your blast radius. And then also make sure that you have a rollback plan. In your mind, you have a hypothesis as to what will happen, but in reality, we just don't know until we run this experiment. So make sure we have a means of rolling back, of stopping that to restore our system to its normal state. So if that means sort of narrowing down the experiment to a certain area, then do that. And then once you have your result, look at how it can be fixed. You know, what can be done to mitigate this from happening. And now sometimes this can be the hard part, depending on cost. There's a lot of things that we'll talk about later as to, to how we can solve some of these issues. Can it be fixed? Sometimes it'll be a case of implementing and refining timeouts between services, rolling out some of these existing resiliency patterns out there. Some of them can be fixed, some of them can't. We'll get onto that shortly. And if they can, rerun the experiment, see what happens again. You know, your second hypothesis is, okay, this should work now, or this should behave in this way. So rerun that experiment and see what happens. Chaos engineering is an iterative process. You know, there's no one-size-fits-all solution. It takes a bit of time. And there are no silver bullets. The people among us, certainly engineers among us, will know that there are always trade-offs that we need to make in what we do. Chaos engineering is no exception. Some of the things you have to think about is we're not all Google. You know, how as a company or as a service, how reliable do we really need to be? You know, do we need 3 nines reliability, 4 nines reliability? As those nines increase, you know, cost increases. You've got the financial cost of, you know, sort of redundancy, additional servers to cope with additional load. There's a time cost involved, the engineering cost as well. So you really have to think about as a company how reliable you need to be in your services and what kind of SLAs do you offer. And you have to ultimately do your cost-benefit analysis. You know, is the cost worth it in the end? You know, if you're running certain businesses, it might not be a big issue if there's a little bit of downtime because other businesses might not depend on it. And no one is invincible to all diseases. Going back to this sort of vaccination analogy, you know, there's infinite variability out there. You can't predict everything. And there's a really good quote by this guy, Sidney Dekker. He's an expert in safety critical systems and is often sent in to do a lot of research into air accidents, the recent BP oil spills. He wrote a really interesting sort of write-up of investigations around there. And in his book, Drift into Failure, he says, everyone can do everything right at every step. And you may still get a catastrophic failure as a result. You know, failure is inherent in complex systems. And you can do everything correctly there along that whole process. Everybody can be doing the right thing, but it can still result in a failure. You know, failures aren't rarely the cause of a single problem. You know, the configuration issue, okay, the configuration went wrong, but what caused that configuration to go wrong? When you start thinking about human influences, why did that human think it was okay to change that, or how did they change that with the wrong value? If you just say, okay, the configuration is wrong, you're kind of missing the other side of that as to how did that get wrong, and you know, what led that to, what decisions and thinking led that to be setting correctly. You know, nobody goes into work with a plan to take down production. There are things that build up to these things happening, and they're not always as simple as just, you know, that failed or that configuration was wrong. So there's a certain level of infinite variability in there, and that's why it's important to also exercise how as a company you recover sort of from the human side with these issues. I alluded earlier that there are certain tools to enable you to run these experiments. And if you're interested in kind of looking further into chaos engineering, I would highly recommend checking out this GitHub repository. It's sort of community driven. It's a fairly new area, and it's growing all the time with interesting talks. So you'll be able to find a lot of the things I talk about in here in this repository. But they've also got a whole huge section around tooling of other companies that are doing this and contributing these tools to the open source ecosystem. Anybody here sort of using Docker or Kubernetes? Oh, fantastic, a couple of hands. One of the great things about Docker and Kubernetes is it's a consistent API that you can talk to. You know, the Docker API is the same for everybody. So in terms of building tooling, there's a lot of tools out there that enables you to kind of intercept traffic between containers, take containers down. If you're not using something like Docker or Kubernetes or other recognized orchestration systems, how you sort of roll these experiments out can differ a bit per organization. You know, if you've got multiple instances of things, it's how you can coordinate those chains across instances. But if you're using something like Docker, Kubernetes, there's a consistent API there, so there's lots of tools around there. One is Pumbaa, for instance, which allows sort of network emulation across containers. Another one is KubeMonkey. It's Netflix's Chaos Monkey, but in Kubernetes clusters. With Chaos Monkey, there are a few dependencies that come along with it, but when you start talking about containers and Kubernetes, you know, there's a fairly sort of consistent API to be able to run these against. And then there are other really interesting ones. A particular one I'm a fan of is ToxiProxy. It's a TCP proxy that enables you to simulate sort of different network states and network conditions for resiliency testing. So, for instance, what you do with ToxiProxy is you spin up a Toxi server. You route your traffic through that. You know, whenever you come to sort of run your experiment, you can start routing components through that. So you can put it in between, say, your EC2 cluster and a Redis cluster. And then what you can start to do is you can set that state, sort of failure states, they're called toxics, I believe, in that server and enable and disable them with a certain level of sort of jitter, which will intercept the TCP traffic going to Redis or your data store or another provider or another service, and then start injecting sort of drop packets and latency to try and exhibit some of these failures you see from systems that are failing slowly or databases with CPU utilization issues. They've also got the means to be able to automate a lot of that as well. So in your testing, in your automated tests, you can spin it up and start to run these as a test suite, so you can have these executed as part of your CI/CD pipeline. And then along with some of these tools, as this is an emerging area, there are companies being formed around this concept and this discipline. One is a company called Gremlin, who are the original creators of Gremlin. They started at AWS, and they left to sort of found this company. And the whole premise of Gremlin is these agents that you install on your machines. And there's some way to sort of coordinate failures throughout your system, so you can target just individual machines or groups of machines from a centralized location and set those failure scenarios such as disk utilization, memory utilization on these instances, and they easily turn them on and turn them off and toggle them and also get all the reporter metrics off the back of it. Any of you remember the recent DIN attack, the DNS attack, which caused massive outages? As soon as these kind of attacks happen and these kind of failure scenarios arise, Gremlin are very, very quick to try and add these as features to their tool set, so you can select from these different scenarios and sort of test your systems against them. So in terms of who's doing chaos engineering, when you hear the name, you initially think of Netflix, but chaos engineering as a discipline has sort of spread much further than Netflix. I mean, there are big names out there doing it, granted, but there are also a lot of smaller names out there, sort of small local companies. It's not just something that are reserved for the big companies. We've got Netflix, Amazon, naturally, you'd expect them to do it, Dropbox, but moving down, we've got sort of smaller, I say relatively small, people like Shopify doing it as well, a lot of other companies. This is very much an emerging discipline that people are sort of beginning to pick up on. We're also starting to see more and more tooling appear from service providers. AWS, for instance, in some of their documentation, they kind of have these class libraries and means and documentation there to show how you can start to inject in failure into some of their client libraries as well. So, there are these APIs being made available that will make this easy for you and running these experiments easier for you. We use, or kind of looking at one particular company that allow you to pass a header, which will then simulate on their end. They'll start sort of simulating network latency as well, so you can start easily building your system to kind of respond and sort of behave appropriately when these latencies occur. So just to wrap up, It's an emerging industry. It is growing. It started off at Netflix, but you're starting to see more and more companies sort of pick this up. I have a bit of a future prediction that I think we'll start to see some of the big providers out there start to provide the ability to regularly fail over and just add in tools into things like AWS add in tools in there that allow you to easily sort of have these experiences, these failure states, but in a more controlled manner. And it's a bit of a prediction, but in the way sort of things are going with services offering this, I don't know. I'm expecting to see it as a discipline, though it's growing. There was a conference this year. I think it's the first or second conference dedicated to chaos engineering. It had a great turnout, so it seems like it's getting bigger. There's a Slack channel as well that I'm a part of. I think it's just chaos engineering. And that's been growing sort of hugely in size. When I originally joined it, when I first heard about chaos engineering, it's just a couple of people. But now it's lots of people working at all sorts of size companies kind of sharing how they do chaos engineering. Interestingly, with Black Friday just having gone, a lot of people on there were talking about the failures they saw and then how chaos engineering helped them through some of the issues they faced. But it's certainly growing, so watch this space. If you're interested in learning more, these are some talks that I would highly recommend. First of all, is the GitHub repository. There's all sorts in there you'll be able to find about how you can roll out experiments, some videos and talks from pioneers in the field. So this one over here, definitely check out. It'll probably contain links to all these other ones. The Richard Cook one at the top there, this was the How Complex Systems Fail. This is the paper I talk about. He does a really great YouTube talk at VelocityConf. He took his learnings from complex systems and sort of recognized we were having the same problems in our industry, and was able to share his learnings there. And then Adrian Cockcroft as well, his stuff is mind-blowing. He talks about this. Originally, he was the head of architecture at Netflix. He was a driver for chaos engineering at Netflix. He's now VP, head of architecture at AWS, and he's got some really, really interesting videos on chaos engineering, especially this talk on dynamic non-events, where he talks about failures that exist. In this particular talk, he talks about an aeroplane that not so long ago crashed as a result, and when people went in to investigate what happened, they break down exactly after investigations what caused this accident. And there was at no point in that whole scenario was there one person that did something wrong. Everybody did something right. They did their job, but it still ultimately led to this outage. And as a result of sort of post-mortems and sharing knowledge, the air industry is growing quite dramatically in terms of safety. He even sort of points out that when you drive to the airport, it's about to go on an aeroplane, you should actually be thinking, my goodness, thank God I survived the trip to the aeroplane, because the road is far more dangerous than flying. And then also, why do things go right is another great resource. There's a bit of a discussion in the safety world, safety 1 versus safety 2, or safety differently, which is kind of a different approach on safety, recognizing that failures and safety sort of incidents do happen, and it's a way of sort of making things go right over just focusing on when things go wrong, which goes off in another tangent of a whole different industry, but really, really fascinating stuff. If anybody's got any questions, I'd love to answer them, but thank you very much.
So just a quick reminder, all the talks are being videoed, so all those notes and links are available afterwards. And our first question goes:
how far have Just Eat adopted this? Has it been since the beginning? Are you on the journey? And what have been your challenges to get everybody on board?
Just Eat, we're still very much sort of at the beginning of the journey. We do things like practicing game days, where you can force failures into your system and sort of give training on how to recognize those issues quickly. As I say, the people problems to how developers and engineers respond to those issues. But in terms of reliably sort of introduce and fail and run these experiments, in my team I'm in, we've run a few experiments in some scenarios, but it's there are individuals that are looking at how we can roll out further into the organization. But there are smaller teams that have been doing these things locally. It's still appearing here and there, but we've got an aim ultimately to try and do this.
Hi. can we integrate it in agile environment of development?
So do you mean automate? So automate it. So there are tools out there to enable you to automate these things, such as the Toxi proxy. Toxi proxy was built around being able to automate some of these things. They've got testing frameworks there to allow you to put it into your continuous integration pipeline and have those tests automated every time code gets committed. It depends. I mean, it depends on the kind of failure scenarios you're trying to test against ultimately. If you want to test for a Redis cluster going down, then those things are a bit easier than testing for some of the large scale things. It's very much a case of looking at what you're keen at sort of testing and then seeing what you can and how that fits into the agile process. There's no one size fits all solution. It does require that upfront investment. But yes and no ultimately.
Hi there. Sort of a chicken and egg situation. You talked about build for inevitable failure. How can you sort of do this before you've got a production system that you then start taking down? How do you sort of start thinking of these ideas when you've got a greenfield system and you want to build for this inevitable failure?
Good question. So as you're building systems, when we talk about sort of inevitable failure, we've got to recognise as we build these systems, as that paper suggests, and we should think that failure is normal. So when these systems are communicating to one another, think about what happens when these fail. How do these look when they fail? What behaviours will they exhibit? What monitoring alerting you can have around there? And is there any way you can automate those failures as well as you're building the greenfield system? That has to kind of be at the forefront of your imagination. That doesn't necessarily mean that, as soon as live start chaos engineering and sort of chaos testing, if you can do that along the way, fantastic. But the best thing to do is to start to think about how these systems talk. Don't just put two systems together. Think about timeouts, circuit breakers, and some of those patterns out there. And then also how they would respond. Ultimately, you can't mitigate all failures. Some systems will go down. So start thinking about how you can gracefully degrade. So Netflix, for instance, even though they invest a lot in chaos engineering, sometimes the answer is when that fails, we have to make sure service B can gracefully degrade. So they show a cached response. Or the personalised recommendations aren't necessarily so personalised to you. So it's a case of sort of starting off and thinking about that as well in the greenfield system.
Hi there. I was just wondering, so Just Eat is quite a cool company. You probably didn't have much resistance from senior management about doing this kind of thing. But I guess some of us working for civil service or kind of older places where we've got legacy systems and legacy management, what's your advice? How do we convince these people that this is a good way to go?
That's a really tough one because it does, in some regards, require a large-scale cooperation, coordination, and agreement from above. You can start to roll it out in smaller teams, though, and you can start doing these things in smaller teams. You don't necessarily have to have buy-in from the whole organisation. If you work in microservice, for instance, then one of the typical patterns you see is how the sort of small pizza teams, you own those dependencies. And if there are areas where you own those dependencies, you can start looking at the failure scenarios between those dependencies and what happens and what tools are out there and what resiliency patterns there are to those sort of communications between those systems. If you've got a large system, then naturally it's difficult to force that onto somebody else, but you can start off small in small teams. That's kind of what some of us are doing at Just Eat. It's not at this moment in time, it's not a company-wide thing. There are people that are interested in that, but that hasn't stopped us as a team from being able to do some of these locally. I hope that answers the question sufficiently.
Hi, suppose you were an agile shop and you're in a position where you're doing very good testing and failure mode identification as part of your agile practice, right?
Sorry, Sir Parkinson.
So suppose you're already doing agile properly.
Yeah.
So you're doing things like injecting latency in environments, and so all the technical stuff is covered. There seem to be two ways of getting into proper chaos engineering. So one is to go to the socio-technical side, and the other is to start doing stuff in production. Where would you start?
I certainly wouldn't start in production. Mm-hmm. I know you know that. There's this whole sort of push at the moment for something called test in production, which is there's a woman called Charity Majors who has a lot of really interesting articles around it, which is a separate subject. I don't want to go off too much off on a sort of divergence, but it's around getting your system in a state where it can reliably sort of respond to outages. There are certain technologies like service meshes which allow you to direct traffic off or sort of send small slithers of traffic to new dependencies or other services to be able to sort of work around some of these issues. That would be an ideal state, but that's a long way off for a lot of people. So the thing to do is to start sort of small, start within your team or in QA environments. Ultimately, if you're doing, well, it depends. I mean, if you're the whole concept of running an experiment too, there's also that side of things as well. Actually, being disciplined and thinking, okay, well, what happens when the system fails? Can we test it? We can put timeouts in to refine things like that and handle sort of latency and so forth. But actually, the discipline of sitting down and running an experiment is another side as well. There's game days as well, where you can, somebody can force a failure on a system and then see how people respond to that failure as well. There are these other areas that you can look at as well before trying to sort of get the whole buy-in from the organisation, because you might, one of the factors is you might not get buy-in from the organisation. Again, it depends on their priorities and how reliable you need to be as well, whether that investment is worth it. Does that answer your question? Yeah, fantastic.
Hi there. If you're not doing this chaos engineering in production, how do your hypotheses compare your QA environment to the production load that you see and the scale of production? Yeah, that's a good observation. At that point, there's nothing like production. You can build your staging environments to mirror production as much as possible, but the fact of the matter is it's not production. So, ideally, you want to get to the point to be able to do this stuff in production. If your system is able to cope with that, that's a great final objective to have and a great place to reach. And there are technologies that will enable that, such as service meshes and things like Kubernetes kind of solve a lot of those problems quite easily. Well, I say easy, but a bit automate some of that stuff. But yes, you're very right there that you can't be 100% guaranteed that what happens in staging will also happen in production. But there are certain trade-offs we have to make, and that's kind of one of them.
Any more for any more? I'm conscious of standing between you and coffee, but no. Okay. Well, thank you very much to Joe for fantastic talk there.